We're here at Google today with Paulo Casanova to talk about graph theory. Paulo, thank you ever so much for having us here. It's great to be here at your offices. So let's start with, what is a graph then?
So a graph is a structure. So it's comprised of nodes and edges that connect these nodes. It's a very general concept. So graphs can be used to represent a lot of things, but in essence, a graph is just an abstract structure in which nodes that we usually, when we draw them, we put them close to each other and draw some lines among them. But in general, they are used to represent any sort of elements and their relations.
Okay, so we can think of a graph as some sort of general computational abstraction. What practical problems can you use this for?
So, graphs can be used to represent a lot of things, right? So, from the, folders and files in your computer,
okay.
Like you have a folder that contains other folders and some files, and then other folders contain other folders. So if you imagine this as a drawing, right, as nodes and edges between these things, they can use
what is the node, what is the edge?
So the node would be either the folder or the file, and the edge would represent containment.
Right, okay, with you now, yes.
So an edge between a file and a folder would mean this file is in this folder. An edge between two folders means one folder is inside of the other one.
Yeah.
So this is one example. Another example would be, for example, in a social network, right, which you can represent friendship relationships. So a node would represent people, and the edge would represent friendship relations. So two people that are friends would have an edge connecting them. And of course, if you think about a social network, then they have all these nodes with all these edges connecting people in friendship relationships. So it's kind of like a gigantic web.
And some of those social networks have the nodes connecting in both directions, that if I'm friends with somebody, they have to be friends with me. And some of them, it only works in one direction.
Mm-hmm.
If I follow somebody, they don't have to follow me back, I guess.
Exactly.
Yeah.
So there are essentially, when you think about graphs, there are two different types of graphs, the non-directional graphs and directed graphs. So in the non-directional graph, there's two nodes, there's a connection between them. So for example, if you think in many social networks, friendship relationships are reversible. So if I'm your friend,
yes.
You're my friend.
Yes.
So it's not a directed relationship. But you think in other concepts, such as followers, for example, I can follow you without you following me.
Quite.
So in this case, the edge have a direction. So, in general, when we talk about graphs, either you talk about directed graphs, in which all edges have a direction, or we talk about non-directed graphs, in which the edges don't have. We never mix them. Otherwise, it's very difficult to work with it. So, when you have directed graphs, you can have an edge going from this point to this point, another edge coming back if you want to have a cyclic relationship, in a sense.
And we can think of the web, I suppose, as pages, as the nodes and the links between pages.
Absolutely, yeah. The links would be the edges on the graphs, and in that case would be directed graphs.
Yeah.
Yes.
Some pages will link back to.
Yes.
Sometimes pages will link back to the page that links to that.
And pages can even link back to themselves. So you can have an edge from one node to itself.
Yeah. But there's no requirement for links to work in both directions.
No.
Okay, so there are special sorts of graphs, I guess, and I think a tree is one. What's the difference between a tree and a graph?
So, a graph is a very general structure, right? So, if you put some restrictions on the form a graph can have, you end up with simpler structures, which are very useful in some situations. So a tree is a specific type of graph in which a node connects to other nodes, right? But these nodes connect to other nodes, but there's no relation between the first ones and the third ones. So you cannot have, say, to think about the family relationship, right? It's like you can be parent of someone, that someone can be parent of someone else, right? But you cannot be a parent of your grandchildren. It's right. So this is what a tree forms. Trees come up very naturally, in a lot of places, and they are extremely used in, I think, all over the place in computer sciences. So, for example, if you think about the first example I gave you about the file system, the file system is a tree, right? You have folders inside of folders and files inside of folders, but a file is not directly inside of the parent of its own folder, right?
Right.
So it has a very specific structure.
Each file is in only one folder.
Exactly.
Okay,
Yeah.
right.
So it forms a very
Each
specific...
file and indeed each folder is only
Yeah,
inside.
exactly.
Yes.
And trees usually have one element at the top, which is the root.
Yeah.
Okay. So it's funny because you usually draw the trees the upside down. With
Okay.
in the real world, the trees start from the
Yes.
bottom and grow up. In computer science, we usually draw them from top to bottom. I think it's just a convention in the end. We're just used to doing things that way. So trees come up in a lot of ways, in a lot of places. So that's kind of the file system is an example.
Mm.
But anything that involves decomposition is usually mapped as a tree. So, for example, if you want to talk about a building, you could say a building contains floors. Each floor contains several rooms, for example, and you can say, well, each room can contain many seats and so on. So, and this maps very naturally to a tree. So trees are used in many places. Another place where trees come up very in a completely different way is when you're playing games. When you're putting computer thinking about games. So board games are the simplest example.
Right.
So if you think about, say, a chess game, right? If you think how the computer is going to, you give it a certain board with the pieces in a certain position, how the computer is going to think, and the way the computer, the simplest way the computer can do this is by imagining, well, what if I play every single possible move, okay? And for each move, I generate a new board with the changed move, right?
Yes,
with the change.
yes.
And then from each board that resulted, I'm gonna plan all possible moves, and I keep expanding this all over.
Until sooner or later you hit a winning move.
And I see, so now I can see if I play this, then this one can play this one, I can play this one, and I can start analyzing the tree to figure out what the best move is.
Yes.
So this is how, this is, I'd say, the simplest way you can make artificial intelligence work in board games.
Find all of the moves and pick the one which is guaranteed to win.
And it's a pure tree from a graph perspective. It's a very simple data structure. But extremely efficient, and even every single board game is implemented backed by a tree. Now we have to be clever about the way we do it, but at the end there's always a tree there.
Wow! Right. Okay. Thank you. So we have this sort of Is it possible to talk about a graph as a data structure? Is that
Yes, the graph is a data structure.
So we have this notion of a data structure which we can use to solve a whole range of different problems. Mm-hmm. I guess there are then algorithms that we can use on these data structures. Can you give me examples of algorithms that we can use to work with trees?
So there are, I think, as many algorithms as problems you can put in graphs. There are, of course, some of the best. Some of the most simple algorithms, and very widely used because they are very important. So two of the most important algorithms is the depth first and breadth first. Okay. So these are algorithms that start somewhere in the graph. So remember that a tree, as I said, usually has a root node. So when you think about the trees, we have a clear starting point. But sometimes in graphs we might not have a clear starting point. So these algorithms start from somewhere we give them, and then start following all the other nodes in the graph.
Right. Why would you want to do that? Why would you want to find all of the things in the graph?
So, for example, there's one of the reasons is to find out partitioning. So, for example, if a graph has many nodes and many edges, we can imagine a graph that we can think that the graph is always connected, but it's not. Sometimes it is not. So, if you think, for example, as a roadmap, which is easily mapped into a graph. If you go into the details, it's difficult to model, but in general, you can imagine as cities connected with roads.
Yes.
You imagine you had all the cities in the world and all the roads between the cities in the world. Okay, it's a huge graph, right? Tons of nodes and tons of edges.
Yeah.
Now the problem is if I start in London, where can I go to? Well, obviously I can go to Oxford, I can go to Manchester, but I cannot go to Paris. There's no road to Paris. Well, there's a train there, but it's
actual roads.
I cannot go to the United States for sure, right? So this puts a very important problem in computer science, which is reachability. So which nodes on the graph are reachable starting from somewhere? So New York is not reachable from London, but Chicago is reachable from New York,
Yes,
okay, for example.
yes.
So this puts this.
Which one can see at a glance if one looks at a road atlas, or especially big road atlas.
Exactly. So this is one example of this algorithm, of the use of these algorithms. Okay. Now, both depth first and breadth first solve the same problem in the sense that they both try to find out all reachable nodes starting from somewhere. Okay. But they do it in very different ways. So in depth first, you pick a node, then you see all the nodes around it. You pick one, okay, you move to that node. And then once you're there in that node, you try to find all the nodes around it, and you move to the next one, and you keep doing this. And of course, you have to keep track of which nodes you're in, because you can. And
then you come back. When you can get no further, you
exactly. Yes. Because otherwise, you could just come back, and it would never end, right? Depth first does this. So it keeps moving as further as it can, and then starts backtracking and trying the other.
Just one layer back up the.
Exactly.
Yes.
So breadth first is different. Breadth first looks at all my children. Okay, all my siblings, all the nodes I can come from, go to from this one.
Yeah.
So by following all the edges. Okay, and then I put them in the list to say, well, these are all the nodes I know of, which I haven't gone through yet. And then I pick the first one and say, now let's move to this one.
Yeah.
Okay, now what are all the nodes I can go from this one? I put them at the end of the list. Of course, I ignore the nodes I've already visited. Okay, and then I jump to the first on the list, which is a node that is connected from the first one.
Yeah.
Okay, so I jump to that one. I see all the ones around that one, okay, and I keep doing this for all the nodes in the list. Right. So both the depth first and the breadth first are going to end up by visiting all nodes that are reachable, but in very different ways. So, for example, on the breadth first algorithm has a couple of qualities. Like, for example, it gives you the shortest. If you're trying to find how to go, from London to Oxford, if there's a direct node edge, it's going to tell immediately, I can do it with one jump. Yes. But if I want to go to say, to Newbury, I have to go to Oxford first. That's assuming that's not how the M4 works, but assuming how the way it works, I would first see, Newbury is not in my neighbors, so I cannot jump from Newbury directly from London. But as soon as I would try Oxford, I would see, I can jump to Newbury from Oxford. And so Newbury is reachable with two steps, with two jumps in the graph. So the breadth first has this good quality, which is it gives you the shortest in terms of number of jumps.
Right.
Now, the reason why I'm putting this carefully is that if you think about roads, right, in the graphs,
it's not necessarily the number of interchanges that matter.
Matter, exactly. So I might have a direct road from London to Edinburgh, but it's still a long trip. Right?
Yes, okay.
So usually, in many useful applications, we actually put weights on these edges, saying, moving from this node to this node has certain costs. Well, cost here can be a lot of things, but for example, think about roads can be distance. So you can say, London to Oxford is like 40 miles, whatever, and for Edinburgh is like 400 miles or another distance.
Or it could also be time for the journey.
Also time
so
for
you might be more interested in the fastest rather than the shortest.
Exactly.
And it's still a number, isn't it?
And that's how a lot of, at the end, a lot of these GPS applications actually work. So when you say, I want to minimize time, then they put time on the graph and compute things. When you put, I want to minimize distance, they put minimize distance on the graph. When it tells the GPS application, I don't want to go on motorways, what the application does, it cuts off the edges that represent motorways and tries to find is the destination still reachable even without it, and so on. So this is kind of the.
I'm always curious about why one would want to.
That's
more user space.
But for example, you can think about you can think if you're doing, for example, here in London, right? You can say, I don't want bus trips, so I don't want to go on the
and I suppose
tube,
there are countries where they charge for motorways and don't charge for other routes, so that would be a factor. Yeah.
So, but these algorithms, breadth first and depth first, do not take any weights into consideration. They're just exploring the graph and giving the set of reachable nodes. Now, there are algorithms that take this into consideration. Probably the most famous of them is Dijkstra's algorithm. He's a very famous man in computer science. And there's an algorithm that is more clever in the sense that it keeps track of the cost of reaching each node. as it follows the graph.
Yes.
And so understands that maybe I can reach Newbury by going to Edinburgh, and then from Edinburgh to Newbury, and this I'm probably going to travel 1,000 miles or something similar or more. But if I go from Oxford, it's actually shorter. Even if I have to do several, if I have to move through more edges, I might end up having a smaller weight in the end.
Right.
Because I might have one single edge that has a weight of 100, and I prefer to go through 3 different edges that have a weight of 30, for example.
Okay.
So this is why breadth first is usually seen as graph exploration, reachability, because most useful applications use with these weights in the graph.
That's interesting. Yes. Yes.
So these ones are many algorithms.
Okay, and you say that there are as many algorithms as there are problems, and I think one of the problems which folks might well have heard of is the travelling salesman problem. Can you explain what that is?
That's a very, very interesting problem, especially because it's, I think, the most typical problem of a huge class of problems, which are the NP-complete problems.
Yes.
So the travelling salesman is a very, very practical problem, which is I need to visit several cities. So imagine this map, right? The graph with cities as nodes and roads as edges, and with weights on the roads. Imagine distance, time, whatever you want. And the problem is, can I visit every city on the map, not going through the same city twice, but covering all of them, and through the shortest possible route? Okay.
Right.
And so the way...
Which is a simple enough problem to state.
Is a simple problem to state. Immensely difficult to solve. So it's usually, if the graph is very sparse, so very few roads, it's very easy to conclude whether it's even possible at all. Okay.
Right.
But if there are a lot of connections in the graph, a lot of roads, it's very simple to come up with a solution.
Right.
But the question is it the shortest path?
Okay.
And that's why trying to find out, what if I, instead of going from here to here, I go to here, from here to here, but then I cannot go back to here, and then so you start finding...
Right, because the contingencies as you close off other possibilities.
And it ends up being a combinatorial problem. So you're trying to, because then each path has its weight. By choosing one path, you cannot go back to that city, so now you've cut off more paths on the graph. You're left with some of them. Some of them might be very heavy in terms of weight. Yeah. So you might want to avoid those, but as you keep trying and keep backtracking.
So even finding... a very naive way of tackling it could be to list out all of the possible routes and simply pick the shortest.
Yes.
But even finding the list of all possible routes sounds as though it's not going to be much fun.
Well, you can try it. So it's an exponential problem.
Of course, yes.
So if you're talking about a problem that has 10 cities, it's really very easy to solve. Manually, you're going to see that it's more difficult than it looks like if I do it by hand.
Yes.
But a computer will solve that one easily.
And that, maybe not 10 cities, but 5 cities is a problem which teachers could set to students.
Definitely. Yes.
Find the shortest
definitely.
route.
Yes. The problem is that when you have 100,000 cities.
Okay. Right,
so, for example...
Will keep the class busy for quite a while.
For eternity, yes. But it's interesting to understand that these problems, NP-complete problems, the traveling salesman. Yeah. So the traveling salesman, for example, particular, is a very actual problem in the area of logistics.
Yes.
Think Amazon.
Yes.
You want to hand out deliveries to someone. You have a van. You have to go to and put the deliveries to people. Well, you want to use the shortest path.
Yes. You want to visit all of your customers within the day, and you don't want to go twice to
the same customer. Exactly.
Yes.
So but the question is, what is the fastest path? And if you think about addresses as nodes in London and all the streets as edges, it's a huge graph.
Yes.
Right?
Yeah.
And now you're saying that I need to visit 20 or 30 customers. So I do need to solve the travel salesman problem, and regardless of the fact it's very difficult.
Yeah.
But it also shows up in a lot of different areas.
Let's take that example then, because I think that's a really interesting one. And you've got the 30 parcels to deliver in the day. Mm-hmm. Is it computationally practical to find the best route? Or are we
No.
satisfied with just a good enough route?
No, we go for good enough.
Okay, even when it's a smaller number
So
of 30.
the problem with I think there's something that is very unintuitive about complexity, about exponential complexity, and the reason is the reason why it's unintuitive is that it's very fast and then suddenly it just becomes. It takes centuries to solve. It's because it is multiplying, right?
Of course,
it's like, and so it's really easy for some of these problems to take a decade. Now, if you want to deliver something the next week, you're not going to take a decade to compute the path.
No,
right?
we both have to set out on the journey.
So that's why we come up with algorithms that use heuristics, which is heuristics is the kind of the I'd say the formal term for doing some guesswork. Like, I think that there's some tricks you can do here, trying to simplify the problem, to make it simpler. Sometimes either by reducing the number of edges, by saying, well, these rows are just too bad. I'm not going through Piccadilly Circus regardless of what I want to deliver, because I know it's going to be huge traffic. There are going to be huge traffic jams there.
Yes, we're unlikely to find a hyperlink.
Exactly, it's hardly going to be so. We can cut off edges. And we can do things like, for example, just partition the graph, saying, well, I'm going to look to deliver someone in this neighborhood, and then this neighborhood, and I'm going to ignore if maybe it's possible that the guy that delivering in the next neighborhood may actually go and deliver something here, because otherwise it's just too difficult to solve the whole problem.
Right.
So we do this kind of heuristics.
Yeah.
That give us faster resolution time, but important.
I suppose this is kind of decomposition if we take the big problem and break it.
Yes, but it's important that you're no longer getting necessarily the optimal solution.
Right.
You may be getting suboptimal
a good
solutions.
solution, but not necessarily the best solution. Okay.
Well, it's typical engineering.
Really nice example. Thank you. Is this something which young people can do practically on computers in classrooms, or is this much more about the fundamental principles, the ideas that underpin this notion of the graph? Can they actually write code for these problems?
Well, I mean, the importance of graphs is the concept and how do you model things in graphs. Now, sometimes I think it's difficult to understand the concepts if you don't try to do this, because that gets very abstract in concept. Now, graphs are not difficult to program. That's the good thing. And if people want, there are libraries that have a lot of things already. Part of the code's already done, and
so
this copy you can reuse.
Implement the algorithm.
You don't need to implement everything. Although I think it's very enlightening to see some of these things running on a computer, because especially because graphs algorithms have a tendency to become immensely slow on big data sets easily.
Yes.
Whereas, for example,
and so you get a visceral sense of this is a hard problem.
Exactly, because you have these modern day computers do millions, hundreds of millions of operations every second. So they do things at the speed which we don't really have insight on.
Yeah.
And anything you do on algorithms on a computer, and if you don't have big enough data sets, they're all going to be super fast. So you can talk about all these things about being quadratic or cubic algorithms, you can talk about all these things, but even anti-complete problems, if you give it 5 or 6 or 7 series, the computer is going to solve it in a blink of an eye. Yeah. However, the interesting thing about graphs and some of these problems, like the travel salesman, is that if you give it 5 or 6 cities, it'll travel in the blink of an eye. But if you give it 8 or 9, it's going to take it 1 or 2 seconds. If you give it 10 or 12, it's going to take like 20 minutes or 30. And if you give it 15, you're no longer going to wait for the result, because you're going to have to go to lunch or go home or something, because the computer is going to take hours.
Yes, because of this exponential.
Exactly, and you have this feeling of how important this concept of algorithms is, and the practical implications it has.
Because this isn't simply a case of building faster computers.
No, because there's no way we're going to solve this.
Yeah.
I mean, we've been solving building faster computers like for the past decades, right? Faster and faster and faster, and the problem is still the same.
Yeah.
The travel salesman has, I think it's from the 1930s, I guess, initially, way before computers. I mean, it's still a problem nowadays. It's going to be a problem for a long time, because it's not about speed; it's about complexity. Yes. So programming these things in the end may have benefits, as it gives you, insight onto the concepts. The programming itself, I think it's not, as a task, it's not a particularly good exercise. Just a programming exercise.
Yeah.
I don't think it's a good way to learn programming, to learn to code.
Fair enough. Thank you. But this concept of the graph as a way of representing the problem matters.
Yes,
as well as some sense of these are hard problems, or these can
Yes.
some of these problems become very, very hard very quickly.
And it's very important for people to understand when you're given a problem, if I can map this to a graph, then all these algorithms are built.
It's a generalization.
Exactly.
Yeah.
So if I give you a problem, like for example, can I, this particular building, for example, has several floors, has some lifts, okay? And there's a lot of corridors and locked doors and so on. So if I give you the problem, can I go from here to the office down there? Okay, how do you solve this with a computer?
Yeah.
If you think, well, can I model this as a graph? If I model this as a graph, then I have the reachability algorithm already defined. I don't need to reinvent them.
Yes.
I just have to build the data structure and then say, run DFS or something like that. So this is why sometimes all this. There's such a huge effort in mapping things as graphs, because then we have the solutions already built.
Yes, yeah. It's really nice, thank you. So I'm guessing that you're drawing on this in your work here at Google. Can you give us some examples of how this is relevant to what you do?
Yes, I mean, so in my actual work, we do tools for Android developers. And so when you want to build an application to then install your cell phone using the Play Store, for example, you have several tasks that need to be done to do this. And these tasks depend on other tasks. So if I want to package something, that something needs to exist. If that something needs to exist, something needs to build it. So this is a set of tasks.
Okay.
And the way we model this is that we create this graph of tasks that need to be executed. And each graph this is a directed graph. Each graph says which tasks need to be complete before I can execute.
Yeah.
And then at the end, once we have this whole graph, we know where can we start.
Right.
We can start on the graph from which that depends on no task. And once we have this one, you can remove this from the graph and see which tasks now have no dependencies. This one, and this one. You can execute these ones, and then so on. And we keep chopping the graph. Let's say to a certain extent. At the end, we end up with the application built.
And this sort of project management task isn't something which is peculiar to app development. This will apply to problems of curriculum design and timetabling and all sorts of things which
any project,
teachers will encounter.
If you look at project management techniques, PERT graphs, dependency graphs, any of these things are usually modeled as graphs.
Right.
So if you to think about, you have a project and you see, want to see what is the critical path, what is the task that if gets delayed is going to delay my whole project, for example, which is the critical path analysis. This is a graph analysis problem. Yeah. And there are, again, algorithms to solve this. Already done.
But this is such a nice illustration of the power of computational thinking.
Yes.
To the sorts of things which are in a domain beyond, I want to say mere, but just computer programming.
That's why I think it's also difficult for people to grasp graphs in the beginning. Yeah. Because you can represent so many things, from social networks to maps to projects, and everything can be not everything, but a lot of things can be modeled in graphs. So many different things. Yes. In this very abstracted structure. Yeah. But once you grasp it, everything then becomes everything is suddenly a graph all around you, and there's solutions for everything around you. Yes. So it's a very enlightening moment once you click and you understand how it's used.
Paulo, this has been so interesting. Thank you ever so much for your time this morning. Thank you.
Thank you.
Don't miss out on Computing at School's great content here on YouTube. Subscribe to our CAS TV channel.